Many of you have likely heard about the Schrodinger's cat thought experiment. It was devised in 1935 by Schrodinger in an attempt to explain the Copenhagen interpretation of quantum mechanics. By extrapolating it to a larger scale, he tried to point out exactly why it was so ridiculous. In physics, mechanics means the study of movement and energy transfer between objects. Newtonian or classical mechanics is what we would use to describe a car rolling down a hill or an apple falling from a tree. However, classical mechanics can only be used to describe objects on a larger scale, the sort of which we're used to coming across in our day-to-day lives. Physicists often work on what is known as the quantum level. This is the scale of atoms and electrons. Classical mechanics can't be used to describe these objects because they're far too small. They appear to behave according to their own laws of physics. This is what we call quantum mechanics. Exactly why classical mechanics and quantum mechanics don't seem to work together is one of the biggest problems in physics today. It's like the holy grail of physics, the search for a grand unified theory. The Copenhagen interpretation of quantum mechanics states that you can never know objectively what is going on in a quantum system. You can only talk about the events in terms of the probabilities of them actually happening. Schrodinger invited us to imagine a cat in a box. Now let's forget all the logistic things about whether the cat can breathe, if it has enough food or water, etc. Just assume that the cat can live just fine in this box. The cat is put in there with a machine that has a 50-50% chance of launching a dangerous toxin into the air, thus killing the cat. Whilst the cat is inside the box, we have no way of knowing whether the cat is alive or dead. A physicist would say that the cat is simultaneously alive or dead, with a 50-50% chance of either. As it has not been measured, the best answer we can give is that the cat is half alive and half dead. Now this is analogous to a simple particle physics experiment. Imagine you have an electron trapped inside a box. Due to outside knowledge, we can infer that the momentum of the electron could be one of many different possibilities. As it hasn't been measured, physicists would say that the electron has all possible momenta simultaneously. The cat analogy then goes on to say that if you open the box, you trigger the poison system and kill the cat instantly. This is analogous to if you open the box and measure the momentum of the electron, you now definitely know which state it's in. You can never go back to the state of uncertainty. The electron definitely has this momentum. The issue I have with this analogy is that people hear it and they wonder what the big deal is. It's like scientists don't know the answer and they're just making stuff up by saying, oh, it's all these things simultaneously. But this isn't true. The unnerving and brilliant thing about quantum mechanics is that you can physically observe multiple things happening simultaneously. In physics, particles are often represented as waves, mathematical models that describe the particle's motion through space. A particle with one momentum has a wave of one shape, whereas a particle with a different momentum has a wave of a different shape. Like sound waves, light waves, or even waves on the sea, where more than one wave is present, they overlap and can interfere with each other, leading to interference patterns. Now back to the electron in the box. Before scientists actually measure what the momentum is, they observe interference patterns coming off the box. This can only happen if there's more than one wave there interfering with each other. If there's only one particle there, where's the other wave come from? The answer goes back to the Copenhagen interpretation of quantum mechanics and the point that Schrodinger was trying to make with his cat in a box. All possible waves physically exist simultaneously inside the box. Continuing with the cat analogy, this would be like hearing the cat meowing, but also smelling its rotting corpse. When the electron momentum is measured, something happens which we call waveform collapse. All the possibilities collapse into the one single definite probability, which represents the true value of momentum. But then the question is, where did all the other waves go? This was the origin of the science fiction concept of parallel realities. When you make a decision, you splinter reality into many different possibilities where everything is played out. When you measure the electron, the momentum waves all split off into their different universes, leaving behind only one wave which represents the true value of the momentum in our version of reality. Of course you can't prove that parallel universes exist, but this is the best explanation as to what happens to all the missing information at the point of wave function collapse. Now all of this draws me to my own analogy, which I modestly call Bacca's piano. Instead of a cat in a box, imagine a tiny adorable piano, a piano so small that it only has room for a single white key. As such, only one note could ever be played on this instrument. You are given a box with one of these pianos in, but you have no idea which note the key corresponds to. You shake the box about a bit, and when you do, you hear a chord being played. This is of course impossible, but what you're actually hearing is all the different possibilities happening simultaneously. In a state of mild concern, you open the box, you find the tiny piano, and you press the key, and the note C is played. But where did all the other notes come from? You definitely heard other sounds coming out of the box. If you then put your piano back in the box, seal it up and shake it again, you'll only ever hear the C. All the other notes have simply disappeared. This is because you collapse the waveform. Personally, I think this better shows exactly how a nerve in quantum mechanics can be, and it also doesn't give the common misconception from Schrodinger's cat that scientists just don't know the answer and just make stuff up. I hope that's been able to explain a little bit about Schrodinger's cat and exactly what it is. If you have any questions about it, feel free to leave comments below.